Okay. So, as I have told before that on Sunday we will discuss tutorials which I have given to you. The problem which two problems which I have given to you for shell and tube heat exchanger using Kern's method and Bell's method. Okay, so I will quickly cover that and then we will start the theory part. Okay, so I hope you have solved the tutorial. Is it?
Yes, ma'am.
So only one or others as well? Okay. So, is there any difficulty which you have faced, or do you have any doubt or so? Yes, anyone? Okay, how many of you have solved exactly, or only one? At least respond. Yes, anyone? How many of you have solved the tutorial, both the tutorials, both the problems? There are only 5 students in the class today, or others are also there with in group or something? How many students are attending today?
Ma'am,
Hmm.
hello.
Yes, Kausu. Yes, Kausu.
So,
Huh.
in problem number one, should we consider ethanol as dilute aqueous or
That is
anything
hundred
else?
percent ethyl alcohol.
Yes, and while estimating the overall heat transfer coefficient, so should
Hmm.
we from the graph should we consider it as dilute aqueous or something else?
No, what you have considered?
I have considered as dilute aqueous and calculate as.
Aqueous, actually, it is 100% ethanol, so aqueous should not be there. Uh, but So that should be, you can consider as that organic. It is organic liquid, and that before what we have discussed for like um, we have discussed around it is paraffin or somewhere. Okay, so like that you can consider, but aqueous actually it is 100% ethanol. So aqueous will be there when some amount of water is there, right? So probably that assumption will not valid over here. Okay,
So we
so
can take
huh,
pure
tell me.
organics or not?
Sorry.
Can you can you take it as heavy organics or not?
Uh, you can consider that as organics because actually there are limited uh, like limited components. Okay, so you can consider heavy organic, and with that, how much are you getting? Have you calculated considering that?
Yes, ma'am.
So considering aqueous, how much you assumed you have taken?
It's 790, I guess. 790.
790. Okay, and considering that heavy organic, have you taken that heavy organic?
No, ma'am.
Okay. Anyone else has done, or only you have done in the whole class? Yes, anyone else? Variety. Kosu, how much you have calculated? Calculated you is how much in your case?
It's 796.425.
And 790 you have assumed.
Yes, ma'am.
Okay, so actually that would be pretty close to what you have assumed. What I have assumed, I have taken that as 575 only, considering that paraffin, and I'm getting 785. So probably in one iteration, it won't be done like that. But if you are getting, because you are getting almost like 796 something, 785, so much difference is not there. And your pressure drop is coming in like less than 1 bar, or what?
It is 1.09 bar.
For tube side, shell side,
In cell site.
or tube side?
Tube side 0.59384.
Yes, so mine is coming 0.559 for tube side, and for shell side, I'm getting 1.14 somewhere. So how you met for shell side, or you have only done till 1.09, what you are saying?
Yes, I have done only till 1.09. I haven't done the iteration.
So what, how you will proceed further? Just tell me. Don't, no need to calculate. Just tell me. How you will bring that pressure drop for shell side in a range less than 1 bar. See, you are getting 1.09, right? And I'm getting 1.14. So the difference is not much. In that case, what you can do, like you can increase either of these, like baffle cut or baffle spacing. Okay, so you can increase baffle cut, initially you must have taken 25%, so now you can take 35%. Okay, so considering that baffle cut increased baffle cut, you can calculate that shell side pressure drop, but you also need to calculate shell side heat transfer coefficient, because it will affect the pressure heat transfer coefficient also, baffle cut. I hope you are getting my point. Whatever parameter you are changing, uh, connecting to that, what other parameters which could be changed, that also you need to calculate. So if you consider baffle cut, increased baffle cut, no change you will observe in tube side, but shell side, both heat transfer coefficient as well as pressure drop will change. Okay, so consider, just take that, write it somewhere. To you can increase baffle cut to 35%, calculate Reynolds number JH and shell side heat transfer coefficient. Okay, and then you calculate overall heat transfer coefficient, and that should be in the range. Let it be 790, whatever you are considering the initial guess, let it be. Okay, do not repeat, because uh, that is like you are getting value with quite close what I am getting, so let it be. uh, so once you do that, you will find that pressure drop for shell side, it will come less than 1 bar. Okay, so just consider that and reiterate only that part. How much? That shell side heat transfer coefficient, overall heat transfer coefficient, and pressure drop of shell side. That's it. Okay, so in that way you can bring your calculations to suitable range. Okay, I hope you are getting my point.
Yes, ma'am.
And others also, if anyone else has solved, please share, please let me know. I'm not getting that whether you people are getting the things or not. And what about problem 2? Is there any confusion in problem 2? uh, any confusion in problem 2? Anyone?
No, ma'am.
Okay, so I think that problem two uh, that you can solve. Just 1 minute.
Excuse me, ma'am. Ma'am,
Yes.
do we have to use this thickness of baffle during the calculation in problem 2?
Thickness of?
Baffle. It is given in the question.
No, no, no.
Yes. Okay, ma'am.
Thickness of baffle नहीं चाहिए. And 1 minute. Thickness of baffle दिया है क्या? हाँ, thickness of baffle 6.5. That is not required. Shell to baffle diametric. Actually, in this problem, many parameters are already given to you. Okay. So the calculations will not be that much complicated. Okay, but in theory class, I have discussed if any parameter will not be given to you, so how to consider that and which from where you can get that data. Okay, so in that way, I hope that you can solve this problem too as well. Okay, so baffle thickness is not will not be considered. Okay. Okay, so I hope you have solved it, and if you have not, please solve and discuss anytime. Okay, I will give you maybe in next class or so tutorials or the problems related to that condenser as well as reboilers. Okay, so let me start the class now. Let me share my screen, then we will discuss. So I hope my screen is visible in PPT mode, that is design of vertical thermosiphon reboiler.
Yes, ma'am.
Yes. Okay. Okay. Thank you. So as far as last class is concerned, in the last class we have discussed the design of kettle reboiler as well as thermosiphon reboiler. And in thermosiphon reboiler, in thermosiphon reboiler, we have discussed the steps which are involved in it. And if you see that when we consider design of thermosiphon reboiler vertically placed, in that case, what we have observed that design procedure is little bit different. We start with the maximum heat flux, and then we will proceed for that recirculation ratio. We need to maintain the recirculation ratio, and it is important to ensure the recirculation ratio to be maintained before proceeding for heat transfer coefficient calculation, because it is natural circulation, so naturally it should move. Okay, so in what condition we obtain that circulation to be occur naturally, that we need to ensure first, and then we will proceed for heat transfer coefficient and other parameter calculations. Okay, so if you if you have gone through the last class, if you have seen that, if you have attended that, you must have seen that to ensure the desired recirculation ratio to be maintained, we first have considered the pressure drop, and that pressure drop will be by two way. One is due to friction, and that too due to friction is can be done in can be done in two way. One way is considering pure liquid, and second way to consider pure mixture. Okay, and then counting of these two and averaging of that, these two will give the pressure drop due to friction, and then we will consider pressure drop due to static head, because liquid or the mixture will always be maintained in the tube, right? And that should be lesser than the available pressure drop in distillation side. So all these we need to calculate uh, to ensure that recirculation whatever we have assumed is valid. Okay, and after that pressure drop calculation will be, sorry, heat transfer coefficient calculation will be done. Okay, so that was the procedure which we have discussed in the last class. Now today we will consider one example to so that it will be more clear to you the design procedure. So the example is like a vertical thermosiphon reboiler is used to produce 6 kg per second of vapor. Okay, so vapor production is 6 kg per second in an arrangement. In an arrangement, the column operates at a pressure of 18 bar, corresponding to nearly isothermal boiling point of 108 degrees Celsius. Okay, so you see the uh, what is given over here, that is, in an arrangement the column operates at a pressure of 18 bar, corresponding to a nearly isothermal boiling point. Okay, so the point is the feed which is entering to the reboiler, that is at the boiling point. So we do not need to worry about the sensible heat, only latent heat will be transferred. And because the component is one only, we are not given with the mixture. Okay, it is only vapor. So that would be isothermal condition. Okay, and that will be in tube side. You remember that when we consider vertical thermosiphon reboiler, then the boiling will occur only in tube side, not in shell side. If it is horizontal, that will be only in shell side, right? So that is in tube side we have isothermal condition. uh, the heating media we consider as the steam, which is also a single component, and that is available at 150, so that is also a isothermal condition. Okay, so both side we have isothermal uh, condition. So average temperature would be nothing but 150 minus 108, that would be the delta T mean. Okay, no need to calculate LMTD and all. Okay, it will be 150 minus 108 only, right? Next, design the reboiler where recirculation ratio is 4 is to 1. Okay, so what we are given that recirculation we consider as 4 is to 1, that we need to ensure, and for that we need to design the reboiler. Okay, so first of all we will see that at what condition recirculation ratio of 4 is to 1 will be maintained, and after that we will proceed towards the heat transfer coefficient calculation. So here we are given that carry out only one iteration for pressure drop calculation. It means the pressure drop calculation we are given, we need to calculate once only. Okay, but I will tell you, if pressure, if recirculation ratio will not be maintained, then how we need to proceed further, because we only need to do the iteration, we only need to do one iteration, right? But as far as design is concerned, the main aim is to ensure the recirculation ratio, and then we will proceed further. Okay, so I will tell you what uh, if in one iteration this recirculation ratio will not be maintained, so what we need to do. Okay, and for that case, uh, we are given some of the specifications like the tube specification and other properties like tube length 3.65, 20 mm OD, 16 mm ID on 25 mm triangular pitch. uh, Enthalpy of liquid is given at 108, enthalpy of vapor is given at 108. So enthalpy of vapor minus enthalpy of liquid would be latent heat of vaporization, and that into 6 kg per second will be the total heat duty. Okay, so that we need to consider. Further, density of liquid is given, density of vapor, viscosity of liquid, viscosity of vapor, condensate uh, coefficient is given, steam coefficient is given while condensing, so that is 8000 watt per meter square degree Celsius. So that is given in for the shell side, not for the tube side. Next, we are given with thermal conductivity of the liquid 0.13, specific heat 2.6 kilojoule per kg degree Celsius it is given, and we are given clearance of shell and bundle, that is 60, that is 40 mm. Okay, so all these parameters are given to you, and we will see how to design the vertical thermosiphon reboiler. Okay. So, you keep on you keep on seeing the steps which are involved in design of thermosiphon reboiler. The first one is to calculate heat duty. Okay, this is not only the this is not the first step for this reboiler. For every heat transfer unit, the first step is to calculate duty. Okay, nothing new. So we are given that 6 kg per hour we need to produce, and this is the thermal this is the latent heat of vaporization. So we can calculate heat duty as 86.8 kilowatt. Okay, and next you need to find out heat transfer area. Okay, so heat transfer area would be the heat duty by the flux, and flux over here is the maximum flux for this vertical thermosiphon reboiler. Okay, actually, the reason to start from here is like um, until unless you will not fix the heat, fix the number of tubes and all, you cannot proceed for heat transfer coefficient calculation, because velocity and all everything you need to decide. Okay, so here what we need to consider that some assumption be required to find out area. Before we used to assume overall heat transfer coefficient, then we calculate the area, but here you value you cannot assume, because you cannot uh, calculate uh, overall heat transfer coefficient until unless you will not maintain the recirculation ratio, and to maintain the recirculation ratio desired number of units are required. So therefore we will start with the with another assumption, that is maximum heat flux, and considering that we will find heat transfer coefficient, sorry, heat transfer area, number of tubes, pressure drop, and then heat that recirculation ratio will be maintained, and then only we will proceed for heat transfer coefficient calculation. So because of that, the procedure is entirely different for this. Okay, so if I'm considering overall sorry, total heat transfer area, that should be heat duty by heat flux. Okay, so 37,900 watt per meter square is the heat flux. Okay, and this is the heat duty which we have calculated just above. So 31.314 meter square would be the heat transfer area. Okay. Okay. So once I'm having the heat transfer area, we will find out the total number of tubes. Okay, and for that, actually, in this case, vertical thermosiphon reboiler, when we are considering it, it will work only with one pass. Okay, no other passes will be considered over here, because we need to maintain the shortest path through which natural circulation can be maintained. Okay, so that should be with one pass only. And here we will consider one pass, so that the tube side will be available at two ends. Okay, and how we will calculate the number of tubes, that will be equal to sorry, number of tubes into area of one tube will be equal to total heat transfer area. This is as per all previous calculations in previous examples. So n would be the number of tubes, but here you need to consider the effective length. Okay, because effective length will only be responsible for heat transfer. Okay, so 3.65 would be the total length, and 50 you will consider, because 20 is the OD of the tube. So tube sheet thickness should be at least 25 Okay, so 50 you need to deduct from here. So number of tubes would be 138.4, and we can consider 139. Okay, there is no need to calculate to consider this as even value. This should be complete number, that we need to ensure. Okay, this should be complete number, but that should be round up. And while doing round up, uh, we don't need to consider even value. We can work with odd value as well, because only one pass is there. Okay, if one to pass or some other more passes will be required, then it should be it should be taken accordingly. Okay, but it should, in this case, because it is one pass, the number of tubes should be odd as well, but the number should be completed. Now, we should consider the complete number. I hope you are getting. Okay, so this is 139. Now, next is to find out the pressure drop for shell side, sorry, pressure drop for tube side, where the vapor formation will occur. Okay, so next step is to find out the flow rates. Okay, and vapor flow rate, which is given as 6 kg per second, it is already given. Based on that, we can find out liquid flow rate, because recirculation ratio is 4:1. Okay, so 1 part vapor and 4 part water, 4 part liquid, sorry, not water, liquid. Okay, so you can consider liquid flow rate as 24, and when the feed is entering at the bottom of the tube, the total 30 kg per second would be the feed in the liquid phase. Okay, however, when it is exiting, 6 kg per second is water and 24 kg per second is liquid, right? And this is the expression to calculate the pressure drop due to friction. Okay, so what we will consider over here, we have two different conditions. One is when the at the entry point we consider pure liquid, and at exit point we consider the mixture. Okay, so we will calculate the pressure drop due to friction considering both situation. Okay, at entry and at exit. Okay, at entry we will have the total flow rate as 30 kg per second, and at exit the total flow rate will remain same. Okay, because mass same mass will exit, but the point is we will have different density. Okay, and the density of mixture we can calculate at exit condition, like 30 kg per second is total feed, and 6 kg per second is the vapor by its density. Okay, all these parameters are given over here, you can see, like density of vapor, density of liquid, like this. Okay, so at entry point, we will consider this density. However, at exit, we consider for vapor. Okay, for vapor 34.8, for liquid 430. Okay, so 6 by 34.8 density of the vapor plus 24 flow of the liquid by density of liquid. Okay, so once we solve this, we will find 131.447 kg per meter cube as a density of mixture at exit condition. Okay, Entry condition density will be 430 only, right? So in this way we can find out the mixture property. Okay, so once I'm having this mixture property, we will find out the uh, pressure drop at exit condition. Exit condition, that is, we are given, we can calculate velocity, uh, velocity of mixture, or velocity of the, what we can say, uh, fluid at exit condition. Okay, so we have considered total flow as 30, okay, because mass will remain same. uh, that is area of single tube, okay, cross sectional area of single tube into number of tubes 139 we have calculated. So whatever feed is entering, it will be divided in 139 tubes, okay. And then 131.45, that is the density of the mixture. Considering that, we can find out the velocity as 8.166. So now at present we are calculating the pressure drop at exit condition. Okay, so this is the density. I hope you are able to follow. So velocity at exit condition 8.166 meter per second we have calculated. We can find Reynolds number. Okay, and Reynolds number over here is, you can see that density of the mixture, velocity which we have just calculated, and di divide by mu. Okay, and if you consider this mu, here we are already given viscosity of the liquid zero point 0.1, and here I, I have been given viscosity of the vapor as 0.05. Okay, so what we have considered over here? Viscosity of liquid, okay, not viscosity of mixture or viscosity of vapor. Okay, the reason being we are given recirculation ratio as 4:1. Okay, so only one part is vapor. Okay, so dense viscosity will be dominant by the liquid. Let's say if you are dealing with the what we can say, low recirculation ratio, let's say 3:2. Okay, in that case, instead of considering the viscosity of the liquid, you can consider viscosity of the mixture. Okay, so in that way you can consider that, you can consider here as well, but that would be more close to the viscosity of the liquid, so that you can, because it will dominate. Okay, so considering that, you can find out Reynolds number at exit condition. Okay, so 1.717 into 10 power 5 is coming. JF you can find out from here. Okay, so 1.7 somewhere here, okay, you will obtain. So it will be coming as 2.5 into 10 power minus 3, right? So in that way you can find out JF, and then you can find out pressure drop at exit condition. Okay, so it is coming as zero point 0.2 bar. Okay, and if you see here, I have considered total length. Okay, because tube side we always pressure drop when we talk about in tube side, the total length we used to consider. Okay, that you also have to consider in shell and tube heat exchanger, either Bell's method, Kern's method, whatever. But for tube side, the pressure drop includes the total length. Shell side will include the effective length. Okay, so at exit condition, the pressure drop due to friction we are getting as zero point 0.2 bar. Okay, now similar calculation we will proceed for pressure drop due to friction at entry condition. So at entry condition, density is density of liquid should be considered. We need to calculate the velocity because it will vary, because density will vary, but Reynolds number will not change. You see, Reynolds number we consider. You can directly consider like this. Otherwise, you may find some variation due to change in decimal values. Otherwise, no variation you can obtain, because that density of density and viscosity both are, sorry, density and velocity both are related, which will counter over here. Okay, so in that case, Reynolds number here you are getting slight difference, but if you see the if you count the decimals properly, no difference you will obtain over here. Okay, so once I'm having the Reynolds number in the same line, we can no need to calculate, no need to find JF again. That will be same as 2.5 into 10 to the minus 3, as you can obtain over here. And delta P for entry condition we can find simply considering total length. Okay, just we have discussed. And pressure drop at entry condition you will get as 0.061 bar. Okay, and zero point 0.2 at exit condition. So we will find out average pressure drop due to friction, and that is coming as 0.13 bar. Okay. Now once you do this, a second step is to find out the uh, pressure drop considering static head. Okay, because the mixture, or we can say the fluid will always available in the tube, so it will create static head as well. So we will consider the rho gh, but because it at exit and entry condition, that density is different, so we will consider that specific what we can say, that specific volume we have considered. Okay, so in that case, this is nothing but the reverse of density. Okay, so that we have just seen at exit condition and entry condition. So static head you can find as 0.08 bar. Okay, so addition of this 0.08 plus 0.13, it will give the total pressure drop in the tube side. Okay, so that should be 0.21. Okay, 0.13 plus 0.08, so that should be 0.21, and that we will compare with the available head. Available head means that will be in the what we can say, that column side. Okay, and we also consider over here that upper tube sheet of the heat exchanger, or we can say the reboiler, should be what we can say in corresponding to the liquid in distillation column. It means both should be aligned. Okay, so whatever length of the tube we are considering, the same length we will consider for distillation side as available length. Okay, so rho gh or rho gl you can count over here. L should be 3.65, and that density of liquid you can consider. So delta pa you can find as 0.154 bar. Okay, and the that for condition to have valid recirculation ratio, this delta pa should be more than uh, this 0.21. Okay, but in this case reverse is coming. Okay, reverse is coming, it means this recirculation ratio is cannot be maintained. How we will consider, how we will proceed further to maintain that. Okay, so what we need to do over here to maintain this, because if you consider this 0.154, that you cannot change, because it will depend the property of the property of the liquid and the length, so that you cannot change, it is already the fixed one. Okay, second is delta ps. When we are considering, it all depends on the property and length, so this also cannot be changed. The only variation you will obtain in delta p f. Okay, or over here delta p average. Okay, in that case, what change you can obtain? If you see this pressure drop, this pressure drop it will basically depend on this Reynolds number. Okay, and that depends on this velocity. So if velocity will be what we can say, velocity will be high, we will have high pressure drop. Okay. But in this case you need to reduce the pressure drop 0.21, we need to reduce, right? So we will reduce 0.13, and to reduce 0.13 we need to reduce the pressure drop due to friction at entry and exit. Okay, for that what we need to reduce, okay, we need to reduce the velocity. And how we will reduce the velocity? When the total mass flow rate will be distributed more number of tubes than 139. I hope you are getting my point. Okay. 139 is total number of tubes, right? Which should be increased so that the total mass, that would be, that is whatever it is, that is 30 kg per second, it will be allocated to more number of tubes. So less velocity we will observe. Oh, all right. So in that case, you need to increase this number of tube. And how we will increase this number of tube? Okay, by increasing the area. Okay, because dimensions are fixed. By increasing the area, we can increase this. And how we can increase this? By reducing this flux, because that is the maximum possible heat flux. We have started with this value. Now you need to reduce this. Okay, because this duty you cannot change. Okay, so you need to reduce the flux to increase the number of tubes, to reduce the velocity, and then to reduce the pressure drop due to friction. Okay, so in that case, what could be the what we can say, uh, the thumb rule to reduce the flux? Okay, I would say there is no thumb rule. Okay, you need to see the values and you need to reduce the flux. Okay, if in this case like 0.21 is much more than 0.15, okay, in that case you may reduce the flux just by, you can say, just by 5,000, then 37,900. Okay, so here you reduce the flux maybe by 5,000, 6,000, or you may reduce this because some difference is more. Okay, so in that case, you may reduce the flux by, let's say, 6,000, or 5,000, 7,000, also, like that. Any value you can do, because I cannot tell you the any fixed value or fixed change. Okay, you need to judge it. Okay, so in that case you need to reduce the flux, then you will find this, you will bring this condition in valid um, region. Okay, like 0.154, that should be more than summation of these two. Okay, so what value you need to reduce to bring this to the valid region, that you need to figure out by iterations. Okay, and while reducing that, there is another point you should consider, because this reduction in flux will increase heat transfer area. Okay, so you need to only increase the heat transfer area, or let me tell you in this way, that you need to only reduce the flux in such a way so that this condition would be maintained. Okay, if let's say you are you need to bring this addition less than 0.154. If it is, let's say, point 15 or 0.145, like that, very less, then only recirculation will be possible. But we will maintain, we will bring it close to 0.154, but not exceeding, right? So the point is, you need to reduce the flux in such a way so that this condition should be maintained. But while reducing, no what don't reduce much, because in that case you can say that condition is valid, there is no point. But the another point is, you unnecessary increasing the area. Okay, uh, because increasing area will direct affect the capital investment. Okay, so you need to consider the design valid, and that economically feasible also. Okay, you will say that, oh, if you reduce the heat flux directly, like 15,000 or 20,000 in one go, okay, you can bring the recirculation ratio within the range, no problem, but you will unnecessarily increase the area. Okay, so in that way you need to reduce the flux slightly, then see this condition, then reduce the flux, then see this condition, like this. Okay, so 5,000, 7,000, like that reduction in one go, that is acceptable. Okay, but if it is like this condition will be well away, then or what we can say, that much more than we need to obtain, then in that way you need to increase the flux. Okay, so just keep in mind that you need to reduce the flux in such a way so that this condition would be maintained. I'm sorry, I'm taking more time to explaining these facts in much more detailed, because that feasibility of the design, in all aspect you need to consider that. You, in that way only you will proceed for good designing. Okay, now, I hope you can bring that to the feasible range. Okay, that would be the exercise for you. Okay, so uh, once you bring this, we assume that in this case we will proceed from uh, this condition onward, considering the same recirculation ratio and same velocity and all. But you need to bring it to the feasible range, and then it should the heat transfer coefficient should be should be done. Okay, now, because in the problem only it is given that one iteration will be required. Uh, if in the exam or so, maybe because of time limit, that type of condition may also be given to you. So you can do that accordingly. Okay, and if nothing is given, you need to bring this condition to the feasible range, and then you need to proceed further. Okay, so let's see further calculations. We need to proceed for heat transfer coefficient calculation. Okay, and as far as heat transfer coefficient is concerned, again I'm having two different condition. One is at entry and second is at exit. Okay, because at entry we are given the pure liquid, and you need to consider the heat transfer coefficient of single phase flow. Okay, as you consider for what like mm, shell and tube heat exchanger. Okay, like that. So you will consider the uh, heat transfer coefficient at entry condition considering single phase, and at exit condition you need to consider two different phases. One is vapor, which is continuously forming by the boiling of the liquid at the surface, so that we consider as nucleate boiling. And then nucleate boiling, we will uh, uh, we will correct that value, okay, by some correction factor, because all these nucleate boiling will be occurring in thermosiphon reboiler in movable phase. Okay, or flow or fluid is already flowing. Okay, so that we need to consider. So one is nucleate boiling, another is convective boiling, because that is the mixture of vapor and liquid. So vapor, for that you have considered nucleate boiling. For liquid you consider, because continuous vapor formation will occur, and it will create convective that heat transfer in the liquid phase. Okay, so you need to consider convective heat transfer, but that too with the correction factor, because that is continuously flowing. Okay, so what is the point to consider over here? We will first calculate heat transfer coefficient at exit condition. Okay, exit condition where I'm having vapor as well as liquid both. So as I have told you that when vapor is there, we need to consider nucleate boiling. So this is the expression for nucleate boiling. Okay, that expression we have already discussed in the, discussed last class. In fact, this we have already seen in kettle reboiler. Okay, so 40 bar is the critical pressure. I think that is not given in the problem. Okay, so 40 bar is the critical pressure, and here you see this is the Q. This is the flux. Okay, so this we have taken as 37900, because that value only we have considered for that pressure drop. Okay, but this value belongs to the value of flux at which your recirculation ratio is maintained. Okay, so in that case you need to reduce the flux, and whatever flux at this condition will be maintained, that you will consider over here. Okay, do not consider 37,900. Okay, the valid q value uh, should be considered over here. Okay, so HNB you can find as 6609.3. Okay, and then you need to consider one correction factor, and that we call as suppression factor, FS. Okay, for this you need to find this 1 by xtt, that is uh, what we can say, the factor counting both the phases, like x divided by 1 minus x. So x should be like your one part is sorry, x belongs to the vapor. Okay, so vapor is 1 and 4 part is liquid, so 1 by 4 you can consider over here. Okay, all these parameters are already given, so 1 by xtt you can find out as 0.94. And uh, once I'm having this 1 by xtt, we can find this convective boiling factor. Okay, that is Fs. So zero point 0.9 somewhere we are given over here, 0.94 something. Okay, so 2.75, that value you can find as Fc. Okay, and that is not Fs, that is Fc. Okay, and for Fs, because you need to consider that suppression factor, Fs. Okay, so that Fs you need to find based on another graph, which is counting Reynolds number liquid Fc power 1.25. Okay, so Reynolds number liquid we need to consider. So this you can see here we have the Reynolds number, but the first term over here is 1 minus x. Okay, you please refer the theory class, okay, or volume 6 book. Okay, so that 1 minus x, so x is the vapor quality, so that should be 1 by 5. So in that way you can consider x value, and Reynolds number you can find as which is equal to 1.38 in 10 power 5. So considering this factor, you can find the Fs value. Okay, and it is coming as 4.9, around 4.9 into 10 to the power minus 10 to the power 5, somewhere over here. Okay, so the value you can find as 0.085 Fs. Okay, so HNB prime you need to calculate considering HNB and Fs, that you can see over here. It is coming as 561.8. HFC prime you can find as uh, HFC into FC. Okay, HFC is the heat transfer coefficient for convective uh, condition in liquid phase. Remember, so that you can find Nusselt number is a function of Reynolds number and Prandtl number. The same expression you can consider over here, and Reynolds number you can find as 1.38 into 10 to the power 5. Okay, so considering that JH you can find from here. Okay, what was the value? 1.38. Somewhere here it will come, like somewhere here. You can see the value. Okay, so JH you can find as 2.8 in 10 to the power minus 3. Prandtl number you can calculate. HFC you can find. Okay, this is the HFC value. HFC prime, that this value into FC, right? 2.75. So you can find HFC prime. Okay, so addition of this HFC prime and HNB prime will give you the heat transfer coefficient at exit condition. Addition of these two, right? However, we need to find out convective heat transfer coefficient at entry condition. And in that case, instead of this factor in Reynolds number, you will consider 1. over here, because at entry it is pure liquid, okay, not the fraction, or not the mixture. Okay, so entry, at entry Reynolds number you can find as 171,749, or this value you can also tally with the, you can also see from the pressure drop calculation. Okay, it is not required to calculate this, okay, because there you have considered at entry condition the pure liquid. Okay, and JH you can see over here. So you can find out heat transfer coefficient as for convective phase, and this should be for uh, heat transfer coefficient at entry condition. Okay, exit condition, this is the heat transfer coefficient. So average of these two will give the heat transfer coefficient uh, of where, of tube side. Okay, where that vapor formation is occurring. Okay, and if you consider the condensing heat transfer coefficient in steam side, 8,000 is already given, so it is also the same type, same magnitude. So coefficient you can find as around 4,000 overall heat transfer coefficient, and that you need to what we can say, compare with the required, and required is the heat flux divided by delta T mean. Okay, and heat flux over here again, at which the recirculation ratio will be maintained. Okay, because we have not done iterations over here, so we are considering the same thing, same flux, but you need to reiterate that. Okay, so actual Q will be counted over here, divided by this delta T mean, and that is because isothermal condition in both ways, so that you can consider as it is difference of these two. Okay, and that is coming as 902. Now, if you consider this overall heat transfer coefficient, this value should be higher than this. Okay, because at least this much heat transfer coefficient you need to, uh, that should be there. Okay, you are getting higher than this, that will be sufficient, that will be okay. So in that way, you need to proceed for the that heat transfer coefficient calculation, and in this way the design of vertical thermosiphon reboiler can be completed. Okay, but you need to iterate for flux. Okay, so that in that way you can consider the design of this, and I will give you the problem probably next class. Okay, now in this way you we have completed the design of kettle reboiler as well as vertical thermosiphon reboiler. Now we will see few points about four circulation reboiler, but detailed designing we will not consider now. So in the four circulation reboiler, you understand that instead of gravity, we used to put a pump to circulate the fluid between reboiler and the that liquid. Okay, so or we can say the distillation column. Okay, boiling liquid usually flows in tubes, and reboiler may be oriented either horizontally or vertically. So in this way, the that boiling will usually in tube side, but we can have the orientation in different way. Okay, because pump is there, so there is no problem for circulation. Pump will maintain the circulation. Okay, but in what condition you need to consider this for circulation reboiler, like when we are dealing with high fouling tendency liquid. Okay, when fouling of the liquid fouling tendency of the liquid is high, we will it is difficult to circulate on its own because of that precipitation. So to reduce the precipitation, the velocity should be higher, and that velocity, high velocity, should be maintained by pump. Okay, not naturally. Okay, so in that case, these units are characterized by high tube side velocity in order to mitigate fouling. So more fouling tendency fluid is there, you need to consider forced circulation reboiler. Okay, Another point is, if you are dealing with highly viscous fluids, highly viscous liquid, and that highly viscous means what? More than 25 centipoise. Okay. If the viscosity of the liquid is very high, in that case, the for circulation reboiler should be considered, instead of kettle and thermosiphon reboiler. So it is, because it includes an additional unit, that is pumping is required, and pumping is not very cost effective. Okay. So it usually give uneconomical, it becomes uneconomical to include pump in that for circulation. Therefore it is only mandatory to use with for circulation, not with others. Okay, wherever it will be maintained, but in that case you cannot deal this type of fluids. Okay, which are uh, which are of very severe conditions. Okay, so in that way you need to choose the forced circulation reboilers. And here I'm showing one table which is which is basically for reboiler selection, in which condition which type of reboiler should be considered. We have kettle or internal. Internal means, remember, in the kettle reboiler we have that vapor liquid separator. Okay, and that will give that very high diameter of shell, and which give high cost. Okay, to avoid that, we can simply put the bundle at the bottom of the distillation column where liquid is available. So in that case, it is called kettle or internal, like, right? Second is horizontal shell side thermosiphon. Thirdly, vertical tube side thermosiphon. And fourth, we have force circulation reboiler or force flow. Okay, so all four type of reboilers are there. I'm having different conditions. Okay, and if you see here, I'm having different uh, nomenclature, or we can say abbreviations. Like B is given for best. If you see here, I'm having this kettle, so B is given over here, that if delta T is large, very small, we have, what is this, that design delta T. In that case, we can consider different type of uh, at different condition, we can see that which type of kettle reboiler work in which category. Okay, like if you see here, I'm having that uh, if you count this B, okay, B means best. Okay, G is good operation and all. It is already given over here. So if you consider, if you count B, B would be maximum in this. Like if you consider this vertical thermosiphon reboiler, that is 1, 2, 3, 4, 5, 6. 6 B best performances are given. So it means, which is not for other cases. Like if you consider force circulation, and if you are dealing with viscous fluid, it is only the B over here. Second B will be for fouling. Okay, as we have discussed. In other cases, it is not uh, that much, it won't give good performance. Okay, so in that case, what we can observe, that vertical thermosiphon reboiler are most versatile to use. Okay, and in the based on this table, you can have the proper selection of reboiler. And this table, it is not given in volume 6, Richardson Coulson, it is given in search book. Okay, so in that way we will complete that the reboiler topic. And we have already completed shell and tube heat exchanger, the condensers and reboilers. And um we need to start another topic, but I think that we will consider from the next class. Okay, so that's all from my side for today. If you have any observation, you please share. And next topic we will start from next class. And tomorrow I will not take the class, day after tomorrow. Okay, so that's all from my side for today. If you have any um, query or any observation, you can share. Okay, so thank you everyone for your patience. Just see you in next class. Thank you.